Hello, sir. Hello.
Hello. Yes, Anu.
Mm, So there was a question in week two assignment. I think question number 9.
Okay.
Can you solve it?
Uh, right now I can't, but I can get back to you. I will give you my email. You can, or you can give your email. I will try to reply it back after the class. That's okay.
After the class?
Yeah.
Oh, okay.
Yeah. After we
Because sir,
at the end we can discuss
the
that
assignment.
question. Yeah.
Okay,
Sure.
sir.
Okay.
Because sir, the assignment deadlines has been passed. So, but I have doubt.
Sure. We can
So,
maybe in next class I can maybe discuss the solutions of the assignments which you have problem. Maybe I can mark on that and then I can discuss. Okay.
okay.
Yeah.
Okay, thank you, sir.
Yeah. Welcome. Okay then. Maybe let's start. So hello everyone. So welcome to the week 3 tutorial of the microwave engineering course. So my name is Ujjwal Singhal and I am a PhD student in Department of Physics ISC Bangalore. So this is our third tutorial session where we try to like discuss any doubt if you have, and we also try to solve some practice problems uh, which will help you to solve the weekly assignment. Okay, so with that, maybe let's first recap like what you learned in the last week. So first of all, you learned about how to write the equivalent voltages and current for TM and non-TM supporting circuits, and then you learned about the N-port microwave networks, and then you learned how to write the admittance, impedance, and the scattering matrix for a given two-port network, and same is valid for the N-port network. And then you learned about uh, like uh, like how do you describe the circuit if it's reciprocal and lossless, like what is the condition if circuit has to be reciprocal and lossless. And the last thing which you studied was the transmission matrix, which is also called ABCD matrix for the two ports. So transmission matrix or ABCD matrix is only defined for two port network. Okay, so this was the things which you learn. And then also you learn like when you are dealing with high frequency, so the common parameters which can describe the circuit are called S parameters, and that we can actually measure in our real experiments by using a vector network analyzer. So that's why scattering parameters are important in order to describe the these microwave networks. Okay, so what I will do today, first we will go through like what are the definition of the various metrics which you have just a minute. Yeah, so first you learned what is the like how to write the Z matrix. Just So what you learn first, like how to write a Z matrix of a given two-port network. So so this is the matrix representation of the same. So you can write V1 V2 in the matrix form, and that is equal to the another matrix which is called Z matrix multiplied by the current matrix. Okay, and similarly same in order to describe the scattering matrix, you can use you can represent them by using this expression. And similarly one can also describe like how to write the admittance matrix or the ABCD matrix. Okay, so what we will do today, we will try to solve the Z matrix of some particular networks, then we'll also try to solve the S matrix for some particular network, and then we will do some problems on the ABCD matrix. Okay, so and let's so this was all about the definition of various metrics which you learned in order to describe your microwave network. And the other thing which you learned, like what are the lossless and reciprocal network. So for a reciprocal network, so our network is called reciprocal if the transpose of your impedance or admittance matrix is equal to the impedance matrix itself. So if this condition is valid, which is z is equal to z transpose and y is equal to y transpose, then you call that your network is reciprocal. Okay. And similarly, in order to describe the lossless network, so for lossless network your z matrix has to be purely imaginary, and same thing is valid for the admittance matrix. Okay, so if the question is asking you in order to tell like whether the network is reciprocal or lossless, so first you will take the transpose of that, and you will see like whether it's equal to the given matrix. Basically the transpose of the matrix is equal to the matrix itself, so then you will call it a reciprocal network. And similarly, for a lossless network, your z matrix, all the element of the z matrix or the y matrix has to be imaginary. So here is a simple example of the same. So basically what you have some z matrix, and here you can see that if you take the transpose of this, then the transpose of this matrix will be equal to the matrix itself, then you will call it's a reciprocal matrix. And similarly you can see that all the elements within this matrix, all the 9 elements of this 3 by 3 cross matrix are imaginary. That's why this is also a lossless network. So therefore for this matrix it is lossless as well as reciprocal. Okay. And the other thing which I want to tell you, like so this is a convergent table, so which is valid for a 2-port network. So suppose you know what are the ABCD matrix of some 2-port network, then what you can do, you can directly calculate what will be the S11, S12 or S21, S22 parameter of the same. Okay, so suppose if you have ABCD parameter, you will use this formula in order to describe the S11, S12, S21 and S22. And similarly if you have admittance matrix, you will use this thing, and similarly for admittance matrix. And same thing follows for all the 4 matrices like scattering matrix, impedance matrix, admittance matrix and the ABCD matrix. So this is just to tell you like if you have one given matrix, then you can directly obtain all the other parameters by using this formula. So the only thing which you have to keep in mind that this is only for a 2-port network, okay, where the characteristic impedance of both the ports are same, which is equal to Z0. Okay. So now what we will do, so first we will try to like solve these 2 circuits. So you can see in the first circuit you have some pi network. So this represent like a pi. If you take Z1, Z2, Z3, it's like a pi, that's why you called it a pi network. And on the right hand side you can see that you have a T network. Okay, so what is our task today? Our task is to write the complete Z matrix of both of these parameters. So basically if here we will solve it for a general case. So that's why I have taken all the Z1, Z2, Z3, all the impedances are different. And similarly in the case of T network also I have taken all the impedances different. So you can see it's ZA, ZB and ZC. So what we will do, we will try to solve how to solve the Z matrix for such networks. And then in your assignment or in your exam you can get same circuit but with different impedances, and then it will be easy for you to solve if you have done it for a general case. Okay, so first what we will do, suppose you have this first circuit which is pi network, and then I want to find what will be the Z11 parameter of the same. So maybe first you can try it, and then we will go step by step in order to do the calculation of all the 4 Z parameters for the pi network as well as the T network. Okay, so first what you can do, you can try by yourself like what will be the Z11 and Z21 parameters of this pi network. Okay, so you can give it a shot, and then we will try to go step by step in order to how to solve the Z matrix of this given pi network. Okay, so maybe you can try first, and maybe you can let me know what is the like Z11 and Z21 of the first pi network circuit. And also feel free to stop me anywhere if you have any doubt. So here again we are doing it for a general case, and then it will help you to understand it better. Then you can do it for arbitrary network actually, if you know the concept how to solve the Z matrix of any given network. Okay, so please everyone try first how to calculate the Z matrix of the first pi network here, which is on the left hand side, and you can let me know what is the Z11 and Z21 of the given pi network. Okay, I will wait for 2 minutes and then I will go through the solution. So I hope everyone knows actually like how to calculate the Z matrix of such networks, right?
Yes, sir.
Yeah, so you are doing right. Like what will be the Z11 and Z21 of the given network? So can anyone tell like what is the Z11 of the first network?
That is Z1.
Huh? Hello? So Anup, you are saying like Z11 is equal to Z1, right? I will say that's wrong, but give it a shot one more time. Like try to use the like try to use these metrics, and like if you want to calculate Z11 use V1 upon I1 given that I2 is 0. If I2 is 0 that means it's an open circuit, like current is not flowing from there, right? So use this fact and try to solve what is the Z11 and Z21 of this. And that's because if you solve you will know where you are facing difficulty, and then we will go step by step in order to solve the problem. So anyone, what is the Z11? Maybe what I will do, first let's go through the Z matrix of the first pi network, and let's see how to find the Z parameters of that, and then later you can try it for the T network. Okay, so let's do that. So first of all, you know that let me just you know that in order to calculate the Z matrix you need to use this matrix representation where you write v1 v2 is equal to square matrix of Z, which has Z11 Z12 Z21 and Z22 elements, and then you can write like Z11 is equal to v1 upon I1 given that I2 is equal to 0, and similarly you can write Z12 is equal to v1 upon I2 given that I1 is 0, and similarly same thing you can write for the Z21 and Z22 given that for Z21 it's v2 upon I1 given that I2 is 0, and for Z22 it's equal to v2 upon I2 given that I1 is 0. Okay, so first let's try to find what is the Z11 of this. Okay, sorry my screen, yeah. So first of all let's try to calculate what is the Z11 of this. Okay, so since you are asking like you need to find Z11 and you are saying your I2 is 0. Okay, so now let's go to this thing, and you are saying that I2 is 0, right? So no current is flowing from here to here, right? So no current is flowing. That means whatever current is coming, it's coming from the first port, and then what is happening, this current is coming and it's dividing into two sections. So one section will be here, let me just take the pen maybe. So current will come here and one will go here, and similarly this current will go here, right? Because there is no current from the second port, right? So what you can do now, so what you can do now, you can now modify your network and you can represent it like this, where you can see I have shown in the figure. So you have first port which has current I1 and voltage V1, and then you have some impedance Z1, and then you have some series impedance Z2, and then you have a Z0 impedance here, which is Z3 here, right? So because now no current is flowing from here, so you can represent the equivalent circuit like this. Okay, so now you can see that basically for port 1 this whole network itself acts as a one load, right? And you can see that in order to find the effective load impedance of this, you can see that both Z2 and Z3 are in series and together they are in parallel with Z1. Okay, so basically you can write for the port 1, basically it's seeing a impedance which is Z effective, and then you can use the formula for reciprocal formula in order to calculate what is 1 by Z effective. So 1 by Z effective will be 1 by Z1 plus 1 by Z2 plus Z3, because Z2 and Z3 are in series, and from there you can calculate what is the Z effective of this. So if you calculate what is the Z effective, then it will be Z1 times Z2 plus Z3 upon Z1 plus Z2 plus Z3, and now you can write V1 upon I1 is equal to Z effective. Therefore V1 upon I1, given that I2 is equal to 0, is equal to Z effective, which is Z1 times Z2 plus Z3 upon Z1 plus Z2 plus Z3. Therefore the Z11 parameter of this given network can be written as Z1 times Z2 plus Z3 divided by Z1 plus Z2 plus Z3. Okay, so this is how you calculate the Z11 of this circuit. So first of all, you just need to keep in mind that your I2 is 0, therefore no current is flowing from here. So whatever current is coming from port 1 is getting divided into two sections, right? And then basically you can effectively treat as a one effective impedance, and from there you can just write a straightforward formula, which is Z effective is equal to V1 upon I1, given that I2 is 0, and from there you can calculate what is Z11. So Z11 you can write like this. Now our other task is to calculate the Z21 parameter. So I hope this is clear, it's straightforward. So now let's see how to calculate the Z21. So for Z21 again, like if you go here, so your Z21 is again V2 upon I1, given that I2 is 0, right? So basically now if you think, in order to calculate the Z21, what you need actually, you need what is the voltage drop V2 across this Z3, right? So if you can calculate the voltage V2 across this Z3 element, and if you divide it by the current I1 of the first port, you will get the Z21 parameter. Okay, so again let's go to how to find the like voltage across it. So again, as I said, so basically your current is coming and getting divided into two sections, right? And basically it's like a current divider. So basically current will first come here from port 1. So current will come from here from port 1, and then it will go through Z1, and then it will go through the Z2 plus Z3. So basically in order to calculate the V2 voltage, what you can do, you can just use V is equal to IR, right? So basically if you know the current, because these two Z2 and Z3 are in series, so basically if you know the current in this section, you can just multiply it by Z3 and you will get the voltage V2, right? Because it's like a voltage divider here. So basically you know voltage V1, and from there what you can do now, you can calculate what will be the drop of voltage across this Z3, which is the port 2 here, because I told you that current is getting divided. And how the current gets divided, so you know that I is V over R. So because now these two networks Z11 and Z2 plus Z3, they are actually in parallel. So basically current going into here, Z1 will be V1 upon Z1, and similarly current here will be V1 upon Z2 plus Z3, right? So basically current is in this section is V1 upon Z2 plus Z3. And now in order to calculate voltage drop, what you do V is equal to IR, right? So basically you know I, what is the current in this section, and then you just multiply it by Z3, and that will be your V2, right? And now what you can do, you can write uh, so basically, if you go back, you know that in order to calculate Z21, you need to know V2 in terms of I1, right? So but here you can see that your V2 is in terms of V1, right? But now, because we have already calculated the Z11, which is equal to V1 upon I1, what you can do, you can eliminate the voltage V1 in terms of I1, right? So basically, if I use the previous formula of Z11, I can write V1 is equal to I1 times this complete Z effective. So if I put here the voltage V1 value in terms of I1, I will get this following expression, right? And now you can see that numerator and denominator are same, like they have Z2 plus Z3, which is common. So therefore one can simplify this, and you can write that V2 upon I1, because now I1 will come into denominator, given that I2 is equal to 0, will be Z1 Z3 upon Z1 plus Z2 plus Z3. Therefore the Z21 parameter of this is Z1 Z3 upon Z1 plus Z2 plus Z3. Okay, so now, like, this is like a simple procedure which you need to follow, right? If you are thinking that your I2 is 0, that means it's an open circuit, and then therefore your voltage will divide. So therefore, in order to calculate the Z21 parameter, you need to calculate the voltage V2 first in terms of V1, and from there, because you have already calculated the Z11, you can substitute V1 in terms of I1 by using the Z11 parameter, and from there you can calculate the ratio V2 upon I1, and that will give you a Z21 parameter. So now can you do the same thing in order to find the Z22 and Z12 for the same? So you can stop me if you have any doubt, but I will urge you to try in order to find what is the Z12 and Z22 of the following pi network. So please ask me if you have
Hello,
any.
sir.
Yes.
Sir, yesterday we have another online session, problem session.
Yes.
Sir, yes, sir. Yesterday, ma'am was saying that this D1 is not a voltage source. This is the voltage across Z1.
Yes.
And sir, yesterday, so sir, today you consider V1 as a source, and you said that this circuit looks like a current divider.
Yes, because
Okay.
should I go through the solution? No. Maybe if anyone is not replying, I will go through the solution, and I will tell you what is the Z12 and Z22 of this, and then you need to solve the same for the T network. Okay. So again, as I told you, first let's calculate what is the Z22 of this. Okay. So again, as we do for the Z11, what you will do now, for Z22, current I1 has to be 0, right? So whatever you did here, the same thing you will do, you will calculate that Z effective, but now you will do for the uh, uh, with the second port. Okay, so again you can calculate what is the Z effective, and now you can see here now your total load will be, your Z1 and Z2 will be in series, and they will be in parallel with the Z3. So therefore you can write 1 by Z3 plus 1 by Z1 plus Z2, because they both are in parallel, and you can calculate what is the Z effective of this. So Z effective of this will be Z1 Z2 Z3 upon Z1 plus Z2 plus Z3. Okay, and now you can just write Z22 will be equal to Z1 Z2 times Z3 upon Z1 plus Z2 plus Z3. So again it's the same thing which I did for Z11. And now in order to calculate the Z12, what you need to know what is the voltage V1, right? So again, now again you need to calculate voltage V1 in terms of V2. So again, if I go here, now the current, your current I2 will go here along the Z3, and it will also go from the Z2 plus Z1 which are in series. Therefore, in order to calculate the voltage V1, you need to calculate what is the current flowing here times the impedance Z1, and that will be your voltage V1, right? So basically you can write V1 is equal to V2 upon Z1 plus Z2 times Z1. Okay, and now you already know what is the value of voltage V2 in terms of I2, right? That we have calculated from the Z22 parameter. So basically you can write V2 is equal to I2 times Z22 parameter, which we have calculated from here. And now if you put this voltage V1, uh, so like you put the voltage value V2 in terms of I2, you will get the following expression. And again you can see that in numerator and denominator you have Z1 plus Z2 common, so it will get cancelled. And then if you divide V1 if you divide V1 by I2, you will get the following Z12 parameter, which is Z1 Z3 upon Z1 plus Z2 Z3. Okay, so these are all the four impedance, all the Z parameters for this particular uh, pi network. And same problems are there in assignment. So basically now if you know the general case, like how to write when you have all three different, and you know all like you know the expressions, then you can just plug the values and calculate whatever Z parameter you need to calculate. So is it clear? Hello? Am I audible?
Yes, sir. Clear, sir.
Yeah, so maybe what you can do now, now you know you have solved just the Z parameter of this pi network. Now I want to calculate what is the Z matrix of this T network. So can you tell me what is the, again, Z11 and Z21 of this, if you have impedances ZA, ZB and ZC? So this is called T network because it's represent like a T. And here you need to tell me again what is the Z11 and Z21 of this. So again I am telling, we have calculated the Z matrix of this pi network, and we have now the general form of all four parameters Z11, Z21, Z12 and Z22 in terms of Z1, Z2, Z3. And now you can apply the same concepts and you can calculate what is the Z matrix of this T network. Okay, again I am telling, these questions are really important, so I will urge you to solve it by yourself and then calculate it for like these arbitrary impedances. And this T network is really simple actually. You can just calculate it by just not even using a pan. You can just, like, you can see it and you can tell actually what is the Z11 directly. So would anyone like to tell what is the Z11 just by looking at this T network? No one? Okay. Yeah, you are right. This is ZA plus ZB. Yeah. So again you use the same concept actually. And now can you tell me what is the value of Z21 of this? And then we can go through the solution. So Z11 you have answered, Arun Raj. This is correct, ZA plus ZB. And you can actually, I will tell you how to, you can directly tell what is the Z11 here. And similarly, you can tell what is the Z22 here also. Now you need to tell what is the value of Z12. Again, you need to use the same concepts, and you need to tell what is the value of Z21 and Z12 of this. Whether Z21 and Z12 are same or they are different. So I have got the answer of Z11.
ZC. So ZC plus ZB.
This is Z11 you are saying, right?
No, sir. Z11 is ZA plus ZB now.
Right. And what is the Z21?
Z12.
Yes, Z21 and Z12, what are they?
Sir, ZC plus ZB.
Oh. How?
No, one second, one.
See, your Z11 is correct. I want to just if the concept is clear, you can actually solve it. I just want to, we are conducting this session so that you can learn and clear your doubts and you can solve more problems, right? So if you are facing any difficulty in solving them, you can just tell me. We can go through it once more. That's okay. T network is really easy actually. Pi was little, you can say, but although this is also simple, but T is really, you can just like Z11, as I told you, Z11 and Z22 are really simple. You can just see them and tell, oh, this is Z11 and this is Z22. I will wait for one more minute.
Z22 is ZC plus ZB.
Yeah, that's correct. And now I am looking for Z21 and Z12.
Okay.
Yeah, you can try. I am waiting. So anyone else want to answer what is the value of Z21? Maybe let's go through the solution for this. So I hope this
Sir, one.
yeah, you can try. I am waiting. If you are trying, that's good actually. I can wait, but you should try and see where you are facing difficulty, because these problems are really easy actually.
I think, sir, for Z12 and Z2 and some value will be eliminated.
So what is the number, whether it will be in terms of ZA, ZB, ZC, right, or just in terms of 1? So what is that value? It's really easy actually. If you understood the pi network, then T network is really easy actually. Maybe let's go through and you need to tell me where you faced problem. Okay, so let's go through that. So first of all, let's just see this network. So if you are calculating the value, which is, suppose you are calculating Z11, right? So you will say your I2 is 0, so no current is flowing from here, so this will act like a open circuit. So it's because it's not a loop, it's open, so nothing will no current will flow from here, right? So whatever current will come, it will go, I1 will so both ZA and ZB will now in series, so it will be like and then it's like this. So whatever current come, it goes in series with this, and now what is the effective impedance? So both are in series, right? So effective impedance will be ZA plus ZB. That means your Z11 is just ZA plus ZB. That's what we used in the previous problem. And similarly, when you are saying about Z22, then nothing is so this will act like an open circuit, and then these two will be in series, right? So therefore your Z22 will be ZB plus ZC. So this is how you can just look at it and solve this Z11 and Z22. Now let's try to problem here. So yeah, so this is how you calculated the Z11. That's I have already told you, like because your I2 is 0, so the ZC will like that this will be like a open circuit, and then your ZA and ZB will be in series. So effective impedance will be just ZA plus ZB, and then you can just write Z11 is equal to ZA plus ZB. Now you need to calculate what is the value of Z21. So again, in order to calculate the value of Z21, what you need? You need the voltage V2, right? So you need to tell what is the voltage V2 given that I2 is 0. So basically what you are saying, what is the voltage drop across this ZB, right? So now you know the current what is flowing. So current from here will be V1 upon ZA plus ZB, right? So whatever current is coming here and going, so that is the current, like it's V1 upon ZA plus ZB. Now what is the voltage drop across ZB? That will be I times ZB. So what is I? I is V1 upon ZA plus ZB, and then if you multiply it by ZB, that will be the voltage drop V2. Okay, the same concept which we used, right? So now as I said, again we need to calculate V2, and V2 will be just again it's like a voltage divider. So you will have V1 upon ZA plus ZB times ZB, and now again you know the value of Z11, and from there you can put the value of V1 in terms of I1 and the Z11 parameter, so that you can get the ratio V2 upon I1, through which you can call it V2 upon I1 when I2 is equal to 0 is equal to ZB, right? Z21. So now if you put all of this, you will get that Z21 is equal to just ZB. So that's what I was looking for. Now you can tell me where where you stuck. Is it clear? It's like the same which we did earlier actually. And now you can calculate what is the value of Z22. So again I have told you Z22 will be just ZP plus ZC, and now you can just calculate the value Z12 also. For Z12 you need to put I1 is equal to 0, and then you need to calculate the voltage V1 in terms of V2 like you did here for the Z21 parameter, and from there you can, if you try to calculate what is the Z12 parameter, you will again get the ZB. So if you write the effective Z matrix, it will be Z1, Z21, Z1, Z11, Z12, Z21, Z22. So your Z11 is ZA plus ZB, Z12 is ZB, and again your Z21 is again ZB, and your Z22 is ZB plus ZC. So this is what Z parameter of this T network, and I guess same problems are there in assignment also. So now if you just plug the value of ZA, ZB, ZC, you can get the effective Z matrix of this same. So please tell me where is the doubt in this.
Sir, clear, sir.
Okay.
In between phone call came, that's what I would not be able to answer, sir.
Sure.
Network is last. That's what.
Sure. So,
Okay.
So basically,
Yes, sir.
yeah. So these are the common problems which you will get in assignment, and same problem will be there in exam. Like if you need to know the concept, like how to write the Z matrix of whether it's a pi network or T network or some arbitrary network. So here we have solved it for a general case actually, where I have taken all threes are different, and similarly I also took this ZA, ZB, ZC different, so that we can get the general expression for a pi and T network. Okay, so now this is how we calculate the Z matrix. Okay, so now let's go and try to calculate the scattering parameter. Suppose if you have a series load and a shunt load, which is like this. So again, as we did, like we tried to find the Z matrix of two networks which are pi and T. Now I am saying please try to calculate what is the scattering parameter if you have a two port and both port are of like Z0 50 ohm. Both ports are like 50 ohm. Sorry, Z0 impedance, which is the characteristic impedance of this port 1 and port 2. And then if you have some impedance in series among the two ports, then what will be the scattering parameter? So I want to calculate all S11, S21, S12 and S22. And similarly, if I have some load which is in parallel, like now it's shunt, it's acts like a shunt. So here it's in series and here it's a shunt, where your Z is connected like a shunt here. And for both the cases, you need to calculate what are the scattering parameters. Again, such problems are uh, uh, easy actually, but again I took this problem so that we can from the scratch we can start and calculate what are the scattering parameter for both the networks. Like I can tell you one simple solution, like suppose for this network, right, you know ABCD matrix, right? So you have already learned in class what is the ABCD matrix if you have some series load, right, that you have calculated, and I can show you that. So this is the ABCD matrix which you get. So 1 Z 0 1, right, if you have some impedance in series among the two ports. Now as I showed you this table, right, now you know the ABCD parameters and you can just plug the value of ABCD here and you can calculate directly what are the S11, S21 or S12 and S22. So that is one way. Okay, but we want to go in a more general way where you know how to calculate the scattering parameters of these if you have some impedance in series and if you have some shunt load that is connected like this. So in both cases you need to calculate what are the scattering parameters. So again, please try it by yourself first, or what we can do, we can just first try it for a series load and then later we can, maybe you can let me know what is the answer of the shunt load. So what do you say?
Sir, first you explain for a series connection.
So this you have studied, right, or no? Like how to calculate S parameter of this. So what will be your approach? Maybe you can tell me like how you will calculate the S parameter here. So you have two ports here, which is the Z0 impedance, and here again you have port which is again Z0 impedance, and then you need to calculate what are the scattering parameter. So maybe as you said, I can maybe first go through the first part where you have some series load here. Okay, so first of all, when you are saying about the S parameters, right, so basically you are saying that if you need to find the S11, you will call it S11 is B1 upon A1 and your A2 is 0, right? That means your port 2 is short circuited, right? That's what you write. So and again your S11 you can write it as V1 minus upon V1 plus. So that is the incoming voltage on port 1 and V1 plus is the outgoing voltage on the port 1. And similarly you can define it as a reflection coefficient, right? Now as you said, your port 2 is short circuited.
Hello, sir.
Yes.
Sir, here V1 minus is
uh, uh, B1 is V1 minus, right, and A1 is V1
V1
plus,
minus is
and divide by square root of Z0, that will get cancelled actually, right?
No, no, sir. My question is this V1 minus is reflected wave or
Reflected,
incident wave?
reflected. V1 plus is incident. So whatever
Hmm.
goes
Okay.
forward is your incident, and what goes backward is V1 minus, right? Your positive direction is the
Now,
forward, and your negative direction is the backward, right?
now it's okay.
Yeah. So here you know that S11 is just a reflection coefficient because your A2 is 0. And now if you are saying that your port 2 is short circuited and it has a characteristic impedance of Z0, then your circuit, so basically you have this uh, first port, and then you have some series impedance Z, and then your port 2 is not now short circuited because your A2 is 0, right? And therefore now in order to calculate the reflection coefficient, what you need to do, you just need to calculate what is the effective load again, right? So again I am using the same concept. So your port 1 has a characteristic impedance of Z0, and now it's seeing this much load, which is Z plus Z0, because they both are in series. Therefore your Z load will become Z plus Z0, and therefore S11 directly you can write it as ZL minus Z0 upon ZL plus Z0. So ZL minus Z0 means your Z load is Z plus Z0. So you have Z plus Z0 minus Z0, which is the characteristic impedance of the first port, and then in denominator you have Z plus Z0 plus Z0. So from here you can directly calculate what is the S11. So if you solve this expression, your Z0 and Z0 will get cancelled, and your S11 will be Z upon Z plus 2Z0. Okay, so this is how you will solve.
So,
Yeah.
the port 2 is short circuited now.
Yeah, port 2 is short circuited. That's why I have connected this.
So, like,
You can see
sir,
now.
that not is my series connection, which
Yes.
is already shown in a figure.
Yeah. No, no.
But
There is no, not in figure,
this
right?
is, sorry, sir, why you connect Z not?
So Z naught. So see, when you are saying, so you can think in terms of, suppose you have some uh, uh, some transmission line, semi-infinite transmission line on port 2 that has a impedance of Z naught, and same thing. So you can consider it like this. I will. So suppose you have, so this network you can treat like this. So you have some Z0 impedance transmission line, and this is your port 1, and then you have Z here, and then you have again Z0.
Okay, then Z not is not written or not
Yeah, so here I am considering,
given
like,
in.
this question I took from Pozar actually. So uh, so I direct, you know, this book microwave uh, engineering, David Pozar, right?
Yeah, yes, sir.
Yeah, so
This is
from
nice
there,
book.
so this is how you represent this. So when you are saying your port 2 is short circuited, that means this is port 1, and then it will see a impedance, characteristic impedance of Z0, and therefore your actual load will be Z plus Z0 here, because now it's a short circuited. Is it clear?
Yeah, yes, sir.
Okay.
Thank you, sir.
Yeah. So here you can calculate what is the value of S11, and that will be Z upon Z plus 2Z0. And by symmetry you can see, because it's a symmetric on both left and right hand side, so your S22 will equal to the S11. So your S11 is Z upon Z plus 2Z0. So your S22 will equal to S11 also. That's by symmetry. Now what you need to find, what is the value of S21, right? So now in order to solve the value of S21, you can write B2 upon A1, where your A2 is 0, right? So again it's an short circuited, and similarly you can write B2 upon A1 as V2 minus upon V1 plus, right? So this is the formula which I am using. And now because the actual voltage amplitude V2 at the port 2, that will be the sum of forward and backward wave, which I can write it as V2 plus plus V2 minus. And because my A2 is 0 and A2 is equal to V2 plus divided by square root of Z naught, therefore my V2 will equal to just V2 minus, because my V2 plus is 0, right? So basically V2 I can write it as V2 minus, And now at the port 1, the total voltage V1, again it will be a sum of forward and backward wave, which is just V1 plus V1 minus. And now from the earlier example, you have already calculated what is the S11. So S11 is V1 minus upon V1 plus. So therefore I can write V1 minus in terms of V1 plus and S11. So if I write V1 minus in terms of S11 and V1 plus, then my V1 plus will come out and I will have 1 plus S11, right? So from there, now you can see that in order to calculate the voltage V2, my V2 is equal to V2 minus, right? And my V1 is equal to V1 plus upon 1 plus S11, right? And again, now you need to calculate, again it's a voltage divider, so again you need to calculate what is the voltage V2 here, right? So again the total current here will be V1 upon Z plus Z0. So therefore the voltage drop across the port 2, as we did earlier, will be just I upon Z plus Z0 times Z0, right? That's what I have written here. So my V2 is equal to V1 upon Z plus Z0 times Z0. And now because my V2 is equal to V2 minus and V1 I have computed from here, so V1 is equal to V1 plus times 1 plus S11. So I can write V2 is equal to V2 minus is equal to V1, which is V1 plus times 1 plus S11, and then you divide it by Z plus Z0 and then you multiply it by Z0 here. So now your S21 is defined as V2 minus upon V1 plus. So if you take the ratio of this, that will be your S21. So your S21 will be 1 plus S11 times Z0 upon Z plus Z0, and S11 you already know, which is Z upon Z plus 2 Z0. So basically you can write S21 as like this. So your S21 will equal to 2 Z0 upon Z plus 2 Z0. And again by symmetry, because it's a symmetric network from both left and right hand side, your S21 will again equal to S12 by symmetry. So again I am using actually the similar concepts, but just the definition of the matrix is changing. So earlier I was using, for Z I was using like I2 is equal to 0, but here when you are dealing with S matrix, when you are writing I2 is equal to 0, that means now your voltage is 0, so it's a short circuited, and when your current is 0, it's a open circuit. So if you use a similar concept like for this series connection, you can get what are the effective S parameters if you have some series load between the two ports. Okay, so again this is a general way to do this, but other way to do this is, you know already the ABCD matrix of this, which you have already done in class, and as I already shown you the table, you can just plug this value of ABCD in the given expressions here. Like S11 is A plus B by Z0 minus C Z0 minus D upon A plus B by Z0 plus C Z0 plus D. So if you put the value of ABCD here, you can directly compute what is the S11. And if you do that exercise, right, if you do that exercise, you will get the similar answer which we have got of S11, S21, S12 and S22. Okay, so again this I have done. So what I will tell you, you can, maybe I will left it as an exercise to calculate the S parameter of this network, which is shown here when you have a shunt load. And similar question is there in the assignment also, right? So now I have told you how to write the S matrix when you have something in series. Now you need to calculate what is the S matrix when you have something connected like this as a shunt, and again it has an impedance Z, and from there you can calculate what are the S matrix. And now another way I can tell you how to solve this. So this is the ABCD parameter of some two ports which you have already learned in class. So if you have some impedance between two ports, then your ABCD matrix looks like this. And if you have some admittance shunt here, like which is has a admittance Y and it's a shunt here, your ABCD matrix looks like this, right? Okay, so now again, if you ABCD matrix you know, again you can go back and calculate what is the effective S matrix of the same. So there are two ways of doing it. Either you do it systematically, like you use the same concept. Like if you are using trying to find the value of S11, you first try to calculate reflection coefficient, and then for S21 you need to calculate what is the, again like we did like this, so you need to calculate what is the voltage V2 minus divided by V1 plus, and if you write those expression you will get the general expression of S21 and S11. So I will urge you to try it by yourself. Okay, so I am leaving it like a exercise, although I have a solution, but I hope this you have understood, and I am leaving this as an exercise where you need to, in the next class you need to tell me what is the effective S matrix of this network, which is a shunt load and it has an impedance of Z. Okay, so I hope this is clear. So what I will do, I am skipping this exercise because I think if you have understood this you will be able to solve what is the S matrix of this. Okay, so now let's come on to the,
I think, sir.
yeah.
I think, sir, in parallel or in shunt loads, we just need to calculate the Z load, which is parallel combination with, I think, in parallel combination of two impedance, Z and Z naught.
Okay, so maybe let's take 2 minutes and please tell me what is the, just tell me what is the value of S11. Because if you
Oh,
calculate the S11 and S21, right, and then it's a symmetric, your S11 will equal to S22 and your S21 will be equal to
yeah.
S12. So can you tell me what is the value of S11 here?
Yes, sir,
Yeah,
definitely.
take your time and let me know what is the value of S11. So what is the value of S11? You were right. Try to use this
So,
parallel thing. You were
so
right.
my S11 is minus Z naught upon me 2Z plus Z naught.
Are you getting like this? Minus Z
This-
naught square upon 2Z Z naught plus Z naught square.
Then yes, then I cancelled Z naught.
No, keep.
My answer is true, sir. Minus Z naught square plus upon me 2Z naught Z plus Z naught square.
Yeah, so you are getting this, right?
Yeah, yes,
Yeah.
sir.
So,
And then I common Z naught and cancel.
yes. So this is the same concept here again, but now this will be in parallel actually. So therefore you will add 2, and therefore the your load impedance will be a parallel connection of Z and Z naught, and then you just write ZL minus Z naught upon ZL plus Z naught, and you will get the value of S11. Okay. Now S21 I am keeping it as an exercise, and so maybe you can try it and let me know in the next class what is the value of S21 here. Okay. So it's really easy actually. Like if you want to do it now, you can also do it. I can go through the solution also, whatever you wish. But it's pretty easier than what we. So maybe let's go through it. Maybe let's complete it. So here again, as you are saying S21, right? So let's go through it. So S21, when you are saying you want to find what is the value of V2 minus upon V1 plus, right? So again you need to calculate what is the voltage V2 minus divided by the ratio V1 plus. So again you do the same thing. First you write what is the total voltage V2. So again the total voltage V2 will be a sum of V2 plus V2 minus. But again as A2 is 0, therefore your V2 plus is 0, right? And now you can also write like your V1 will again be equal to V1 plus times 1 plus S11, And now you just need to tell what is the voltage V2 here. So one thing, because now they both are in parallel, right? So whatever voltage is across Z, the same voltage will be across the Z naught also. So basically your V2 minus will equal to V1 also, because it's in parallel, so your voltage will be same, right? So from there you can see, now you can just calculate the ratio V2 minus upon V1 plus, and you will get just 1 plus S11. So now S11 you know, so you can just put the value of S11 here, and you will get the value of S21, which is 2 times Z0 upon 2Z0 plus Z0 square. And again because it's a symmetric circuit, so your S21 will equal to S12. So again, it's you, if you think, we are using the same concepts in every question, where we are just, sometimes we are short circuiting, sometimes we are open circuiting it, and then we are just applying some Kirchhoff's law formula in order to solve the problems. Okay, so again, if you like understood it, I will try to I will urge you to try it by yourself, because again, these are, so whatever problem I have done here, you can find them in assignment also, but here I did them quite general, like assignment is asking you just to find the Z21 or Z11. Here we have calculated all the 4 parameters for both the pi and t network, which is again important. And again, we try to calculate what is the scattering matrix when you have some series and shunt load between the two ports, and that's what we did here, and we got the general formula of all the scattering parameters for both series and parallel loads. Okay, again, this type of problem is there in assignment, the second one. First one is not there, but I included it so that you know how to calculate the S parameters for any arbitrary circuit. Okay, so this is the one thing. So this is how you solve the S parameters. Now let's come to ABCD parameters. So for ABCD parameters, right, so you have already learned in class, so if you have some uh, impedance Z1 that is between two ports, your ABCD matrix will be like this. Similarly, if you have a connection like this, second connection, your ABCD parameters takes these value. And suppose if you have some transmission line of some particular length L and characteristic impedance Z0, then your ABCD matrix can be written like this. So if you know all this, right, so because I told you, if you know the ABCD matrix of first part, right, you can calculate directly the scattering parameter by just using that formula which I showed you in table. And similarly, if you have some parallel connection, then also if you know the ABCD parameter of this, you just need to write y1 is equal to 1 by z, and there you can again write the scattering matrix. So as I told you, there are two ways to solve it. Either you first write the ABCD matrix and then use those formula, or first you do a general way, you just go in terms of voltages, and then you express your scattering parameters. So there are two ways, but I will urge you to go first in a general way to get more understanding, like how to calculate the scattering parameter of these series and shunt load. Okay, so now after this, let's come on to the this part. So this is one of the problem is from the last year assignment. So here you need to calculate what is the ABCD matrix. Suppose you have two ports here with which has characteristic impedance Z0, and again you have one port on the left which has a characteristic impedance Z0, and one port is on the right which has a characteristic impedance of Z0, and in between that you have some lambda by 4 section which has a characteristic impedance of 2Z0, and then it is short circuited by a stub which is again has length lambda by 4. So I just want to know, like, how you will solve such problem if you know these concepts. Anyone? How to solve this problem?
Sir, I think 2Z0 and Z0 is still be in parallel.
In but here you need to calculate ABCD matrix, right? So like how you will
Because beta L will be
So what is your approach here,
Mhm.
like how you will approach it? So it's like a section of transmission, right? So in order to do that, in order to calculate the effective impedance, you need to use the formula of input impedance. Like what is the input impedance if I have some short circuit at a length lambda by 4, right? You can't directly write the impedances because it's a transmission line, and impedance actually varies across the length of the transmission line, right? So such problem is there in assignment also, but it's this is better than that. So if you can solve this, then you can solve the assignment one also. I just want to know like what is your thought about it. And I can tell you, you need to use this uh, like formula. So if you know what is the ABCD matrix of a transmission line of length L and characteristic impedance Z naught, so you can use this formula in order to solve this problem. But I want to know how we can use the same formula in order to solve the ABCD matrix of this. Anyone?
Hello, sir.
Yes.
Sir, that matrix formula cos beta L J, is it not sin beta L?
Yeah.
Beta L we have to find out, no, sir. 2 by lambda. L is lambda by 4.
No, but it's
No.
not. It's for just a section of transmission line, right? But here you can see you have some section and then you have some stub here. So how you will like like simplify this network? That's what I want to know.
Sir, I think the right hand side Z naught is parallel in series connection with two
No,
Z
no.
naught,
See, you are
and
getting confused.
and
So these are the port impedances, right? These are the port impedances. This you don't need to worry about, right? Because what you learned in the your lectures. So suppose you have two ports which has an impedance of Z naught. Both have an impedance of Z naught. And now if you connect some basically series impedance, then the ABCD matrix of that particular network is like this. And if you have some shunt admittance, then your ABCD is like this. And suppose if you have a transmission line between those two ports, then your ABCD matrix is like this. So now you can forget about like these are the ports you don't need to worry about, but you need to worry about what is there between two ports. So you need to simplify this
sir,
network, right?
sir, I think two Z naught and Z naught is in parallel.
But it's like how you can, this is a like you can't define the exact impedance here because impedance varies across the transmission line, right?
Yes, sir. So
Yeah.
this is problem.
Yeah, maybe let's go through it and then. So suppose now you know this is okay line, this like if you have a lambda by 4 line and it has a impedance of 2Z naught, like suppose the shunt is not there. Suppose like maybe let's just suppose this shunt is not here first. Maybe suppose this shunt is not here, then your so your impedance is
Sir,
hello.
sir, characteristic impedance of lambda by 4 is it not which is equal to root of Z in Z or no?
Huh? I am not able to hear you. Can you repeat again?
So the length of the lambda by 4
Yes.
input impedance is
Yes. What is
like,
the, yeah, you need to
is it
calculate what is the input impedance that will be seen here between these two ports due to, because it's like because when you are connected to line, you can say your load impedance is short circuited, your ZL is 0. So how does the input impedance behave when you have a short circuited at a lambda by 4 length? So what will
is
be
it not is it not which is equal to root of Z in Z r, sir? From that we have to calculate, no?
maybe let's I will go through the solution and then we can. So
Sir,
first
I think the impedance will be J Z naught tan beta L.
yes, yes. For this, like I want to ask what is the input impedance here between these two. Like I want to, so you have some short circuit is stub. That means your Z load is 0. So I am asking what is the input impedance of this short circuit when you have a lambda by 4 length. So what is like If you have a lambda by 4
They
length,
did, they did not 10 beta.
yeah, but now if you put beta is equal to 2 pi by lambda and L is equal to lambda by 4, what input impedance you get?
Infinite, sir.
Yeah, so that means it's not here actually, it's a open circuit. This will see it's a open circuit here, right? It's a open circuit. Your Z
Yes,
input,
sir.
yeah. So basically what it remains in the end, it will never see this because it feels like an infinite impedance, like a open circuit. So in the end this problem is like very simple, like what I said. So you have two ports, and in between then you have some transmission line of length lambda by 4, and then characteristic impedance 2z naught. So this, so now you have modified your circuit by saying that because it's a lambda by 4 short and it will modify it to an infinite input impedance, that means it's an open circuit, it's not there, so this is not seen by the transmission line. So basically my whole question remains like this, just my z naught is now 2z naught and my L is just lambda by 4. So now if you put the value of z naught is equal to 2z naught and L is equal to lambda by 4 here, you will get the following ABCD matrix. Did you got it? Like how?
Yes, yes,
Yeah.
yesterday we are facing problem in this type of.
So you got the idea, like because you need to, like whenever you see this lambda by 4 stub, just try to calculate the input impedance, and if it's coming infinity, that means the open circuit, it's not even there actually. So transmission line will see nothing, so it just like a standard problem, like if you have some transmission line between two ports, so what is the ABCD matrix, and the formula for that you have already learned in class. It's just that your z naught is equal to now 2z naught, because this has a characteristic impedance of 2z naught, and your beta and your length is lambda by 4. So now you can just put the value. So this is the formula. If you get after you just put the value of z is equal to 2z naught, and L is equal to, and because your length is lambda by 4, your beta L will be pi by 2. Therefore your cos beta L will become 0 because cos pi by 2 is 0. Sin pi by 2 will become 1, sin pi by 2 again will become 1, and it will become 0. So your ABCD matrix will be 0 upon iota times upon 2z naught, and this 2 iota z naught upon 0. So in what I remember in your assignment, you have just a stub here. Okay.
Yes, sir. Can you check it? Can you check the assignment question? I think
I can give you a clue. I have solved that, so it works. I can
no,
give
no,
you a
sir.
clue.
Sir, I think some values or some part is missing.
No, it's correct only. You are saying about the same expression where you have such circuit, right? So there you have like this circuit only. There is no this part. No, this part is not there, right?
Hmm.
Yeah. So how you will calculate this? Can you tell me? It's really easy actually. Everything is here.
So, sir, when you draw these circuits, in this figure, there is no transmission line. Huh?
Maybe.
I think.
So let me just. So here there is no transmission line. You can suppose this transmission line is not here. So between two port,
Mm-hmm.
you just have this stub.
Yeah, yes, sir.
Yes. Now I am asking how you will solve this problem, and that's pretty easy actually. Everything is here. I am waiting for your answer, like how you will solve it. Again, you have some
I
stub
think
here.
this is a shunt
Yes.
register type of.
So I can give you, again you calculate what is the input impedance. Okay. But now you can think it will be like this network here after you have calculated the input impedance, right? The second.
No, can you now it's okay, sir.
You got it, right?
Yes, sir. If we have no transmission line between two ports, then
It will be like a shunt.
and
Yeah.
step is
Second wala.
connected in.
Parallel.
Okay.
Yeah. And then you can use this. So remember, when you are solving, so one thing I want to highlight. So suppose what I was saying, just a minute. Huh. So whenever you are solving here, you are calculating z, not y. Okay, remember, when you are calculating z input impedance from here, you will get z, right? And this formula is for y. What you need to do, you need to write y is equal to 1 upon z, and then you use the ABCD matrix. Got it?
Sir, what will be the value of beta?
Where?
Oh, sorry. Beta will be 2 by lambda.
Yeah, and
Beta
length is
will
given to
be
you
2 by
actually.
lambda.
I think maybe, if I am not correct, let's solve it. So suppose you have maybe let's solve it. Okay, let's solve it. So again, you have two ports, and I want answer. Okay, like you need to tell me these are the port, and then you connected one stub, and then this is the other port, which is again z0. Okay, so there is no this part, this transmission line is not there. And now suppose again it has some impedance of 2z0. Suppose like this stub has some characteristic impedance of, maybe, let's simplify, let's take it z0 only, but it has a length of lambda by 8. Okay, now can you calculate what will be the input impedance if you have some lambda by 8 length transmission line which has load impedance of 0 and characteristic impedance of z0? So from there you can calculate some number, right?
So Z in which is equal to Z naught. Tan 45 1 value.
Yes, yeah. So I am just trying to give you a hint. I don't want to solve it. I am just saying, so you can just calculate what is the effective impedance, input impedance, and that network will be like this. And that network will look like this actually. Like this, right? True or like not true?
No, sir. It is true because my transmission, my whole structure will
Look like this only in the
looks
end if
like
you
this.
yeah, but the only thing I am
But
saying, this is for y, right? But you have z.
huh,
So what you can do,
yeah,
you just
okay,
write
sir.
y is equal to 1 upon z.
One Z, okay.
So you
Sir, my
replace,
question is this.
yeah,
Sir, my question is this. A and D same. A
yeah,
and D
because
same
they are
because of
not
cos
enough
beta n. Okay.
yeah, just y will become 1 by z. That's what I am saying.
Hmm.
Yeah,
Okay, sir.
got it. Because a and b are constant, a b d are constant, so they are independent, they will not change. So I have solved this problem using this. You can try to solve it, you will get the answer actually. Okay, is it clear, right? How to solve such problem? If anyone has doubt, I can explain once more, but keep in mind, if you
Yes, sir. Yes, sir. Can you explain it again?
again, okay, so you want to understand this assignment wala problem, right? Or
Sorry, sir.
assignment problem you are asking, right?
No, sir. My question is not an assignment question. I'm just saying that, sir, A and D same. A is equal to cos beta L and D is also equal to cos beta L. Okay.
See, you are again
Hello.
mixing, you are mixing two things now. See, the question we did here, okay, so the question we did here, here was a transmission line, series transmission line, which has a length of lambda by 4 and impedance 2z0, and then is also have some stub. Okay, got it? But what we found,
Okay.
this stub is like a open circuit, so effectively your network was looking like this actually. This network was looking like this only. True or false?
Yes, sir. For first condition when there is a transmission line between two poles.
Yeah, but now the assignment question, there is just a stub, there is no transmission line, right? So when you are calculating your input impedance, your network will look like this second wala part, because there is no transmission line in series. You have some parallel shunt there.
Oh, okay. I understand, sir.
You got it, right?
Okay. Thank you, sir.
Yeah. So
Yeah.
one thing also again I want to mention, for this problem, suppose your length is some lambda by 8, suppose, okay, then in that case your input impedance will not be infinity, then your circuit will look like this actually. you have some Z here, and then you have some transmission line here. True or false? For this, if your input impedance is not infinite, it has some finite value, then again it will act like a shunt. So effective network will be, you have shunt also and then series transmission line also. Got it?
Yeah, yes, sir. Yes, sir.
Yeah, and you know
Sir,
how.
thank you so much. Thank you so much, sir.
And you know now, so you have also learned about the cascade networks, right? So for a cascade network,
Yes, sir.
if you have two network connected to each other, you can just multiply the ABCD matrix individually of those networks, and you can get the final ABCD matrix. So this I am just telling for the, like, you will never get this such problem. I am just telling you for the understanding, like, because here the Z input impedance is 0, that's why you don't have here this here Z here. It's just a some transmission line in series. But I am saying if it was not infinite, then you have some shunt part also here, then effective circuit will get modified. And for that we need to see how to calculate the ABCD matrix if you have both parallel as well as a series connection. And one way to do that is to use a cascade network theorem, which says, like, you can just multiply the ABCD matrix individually of both of these network and you will get the final ABCD matrix. So that is for, like, that will not come, but just I told you for your understanding. This is clear, right? I can go. I hope this assignment wala is also clear, the problem. So again I am giving a hit for the assignment problem. Try to use this second part which I have shown. Just remember, this is y. So if you are computing the z, so you need to write y is equal to 1 upon z. Okay, so this was the ABCD matrix, and now this is the last problem which I have prepared. So for a two-port network, you have this following scattering matrix, and determine if the network is reciprocal and lossless. So now you know, like, I can again go on the first slide, right? And here you know, for the reciprocal S matrix, your S should be equal to S transpose, and for lossless your S has to be unitary. That means S times the conjugate of S should be identity. So here you need to use the same things, and you need to tell me whether this network is reciprocal or lossless. Can you solve it? This is just some S matrix which has 4 elements. This is for some two-port network, and you need to tell whether this network is reciprocal or lossless. Again, same question is there in the assignment also. You are solving it, right?
Reciprocal, sir.
This is reciprocal.
S which is equal to S transpose.
Why? This
Sir,
is
S which is equal to S transpose, no?
okay. Let's check. I will go through the solution. Any other answer?
No, sir, no, sir. Here 45 is there, here minus 45 is there.
Yes. So these are complex. These are complex. So
Yes, sir. Non-reciprocal lossy.
This is lossy. Okay, correct. So let's go through the solution. So again, you can write it in terms of this, like your, because the S11 has 0 phase, so it's a real quantity. You can write it as 0.15. Your S12 is 0.85 times e power minus iota theta, and theta here is pi by 4. I can write in radian, and similarly I can write this S21 as 0.85 times e power iota pi by 4, because phase is positive here and phase is negative here, and similarly S22 is just 0.2. Okay, so now in order to be reciprocal, your S should be equal to S transpose. Okay, and you know how to take the transpose of some square matrix, right? So now if your S is equal to S transpose, then only your S is symmetric. So if you take the transpose means you like just bring this 0.85 here, this wala row wala 0.585 in the column, and column goes into row, and this will be your transpose. And now you can clearly see that your S is not equal to S transpose, right? Because you can see here you have a e factor of minus iota pi by 4, here you have a factor of e power iota pi by 4. That means it's a non-reciprocal network. And now in order to be lossless, what you do, your S times S star, that means the complex conjugate of that should be identity. And now if you take the complex conjugate of this, basically you replace iota by minus iota, right? And if you now try to calculate S star by first doing the conjugate of this, then you will not get identity. That will not equal to a identity matrix. That means S is not uh, lossless, so it's a lossy line. Okay, so same problem, this again I have taken from Pozar book. So, and it's a solved problem there, so if you want to go, you can go and try to solve it. So I hope I in this tutorial I tried to cover actually all the assignment problems, not directly but more in a general way, so that you can know like how to calculate S parameter, Z parameter or ABCD matrix for any arbitrary network by using just some simple concepts. For example, like if you know these are really much helpful if you can remember. These are like these are easy to remember, right? So if you can remember this, you can actually uh, compute all the ABCD parameters question. And similarly, we covered like how to find the S parameters in when you have a series and shunt load, and same problem is there in assignment also. And similarly, we understood how to write the Z matrix when you have some pi and t network. Okay, so this was all about the today's assignment, and I actually tried to cover all the assignment problems just to give you a hint. And now you can actually, if you have understood it, you can go and try to solve the assignment and you will find it easier. Okay, so if you don't have any doubt, then we will conclude this session and we will again meet next Sunday, which is I guess 20th August, at the same time from 5 to 7. And if you have any problem, like any question you want me to discuss in the next class, you can let me know. I can actually solve it by myself and then we can discuss it together. So if you have any
So
problem,
can you give your email ID so that if
yeah, yeah,
we
sure,
have I have any problem, then I can send
sure,
you.
yeah, for sure, take this.
Okay, okay, okay.
Yeah, I have typed it in my chat box. You can, if you have any problem, you can just
Yeah, okay, sir.
mail
Got
me.
it. Thank you, sir.
You can just let me know this is the assignment number, this problem, and I will check it and reply it instantaneously. Okay.
Oh, okay, sir. Sir, today's session is so energetic.
Yeah, I think I took difficult questions. Maybe that were they were too, but I think if you can solve this, I can assure you like you can solve all the assignment problem. You will find assignment easier actually, because these are the more
Yeah, yes, sir. Because the concept is so clear now. Today's session is so uh, energetic, sir.
Okay. Thank you, it's a nice feedback.
So thank you. Is it uploaded on YouTube also? Because I joined late, so I missed some
I will
content.
just upload it by night.
Okay, sir.
Okay,
Thank you. Thank you.
okay, okay then.
Thank you, sir.
Yeah, welcome. Okay, I will see you all next time. Bye.
Okay, okay. Bye bye, sir.
Bye.